Hello guys, so in this video we're going to go over how to find the tangent, plane, and linear approximation of multivariable functions. So note right here we have a multivariable function of z is equal to the natural log of 2x plus y at a point P of -1 plus 3, -1x plus 3y. And here we have a formula which we're going to use. So we know that the partial derivative with respect to z of xyz, z minus z naught, is equal to partial x, xyz, x minus x naught plus partial y, xyz, y minus y naught. What do those xyz's mean? Those are the points that we're going to plug in, which we will get to right now. So for step 1, the first step we do is we find the partial derivative of the multivariable function of xyz. So that's step 1. So basically what we do is we find the partial derivative with respect to x and with respect to y of this function. So f of x, f of y. So how do we compute this? Well, understanding that it's a natural log, we have to recall from Cal 1. And if you don't know this, I have a video on how to take any type of derivative, but this is a natural log derivative. So we know that the natural log of u, the derivative of the natural log of u, is equal to u prime over u. So whatever our u is, take the derivative and divide it by the original function u. So now, this is the equation we're going to use. So without further ado, we're going to do this with respect to x first. So partial derivative with respect to x. I always like to set up the f, g, f prime, g prime. You don't have to if you know how to do it right off the top of your head. I think it prevents a lot of error. What you will come to realize is that applying the chain rule will give you the same exact answer, because this is just basically a derived form of the chain rule, the natural log derivative. So what is our x? Our f is the natural log of u. Our g is u, which is the inside function, which would be 2x plus y. So right now we're focusing on just finding the partial x and partial y. So f is the derivative of u prime over u, because the derivative of natural log is u prime over u. So here we're using the chain rule, and the natural log is giving us the same exact thing. So g is the derivative of 2x plus y. With respect to x, we take the derivative of x, which is just 2. The derivative of y, the constant y, is 0 because it's just a constant. So our f of x, the partial derivative with respect to x, is our numerator 2, which is our u prime, divided by u. U is 2x plus y. So this is equal to our partial x. So I'm going to draw this blue dashed line. So now that we have the partial derivative with respect to x, the next thing we're going to do is we're going to find the partial derivative with respect to y. So basically we do the exact same thing. So with respect to y, we know that it's a natural log. It's the exact same function, except now we're deriving the y instead of the x. So applying the chain rule, which is the same thing as the natural log of u prime over u, where the natural log derivative is equal to u prime over u, we know that f is equal to natural log of u. G is equal to u, which is 2x plus y. We know f prime is the natural log of u derivative, which is u prime over u. And then we know that g prime, when we take the derivative of the y term of u, of g, is the y. So derivative of y with respect to y is just 1. So the partial derivative with respect to y is u prime over u. And what's our u prime? Our u prime is 1. What's our u? Our u is 2x plus y. So now 1 divided by 2x plus y. So this is our f of y, our partial derivative with respect to y. So now that we have those values, I'm going to go ahead and make note of them over here. So we know f of x is equal to 2 divided by 2x plus y. And then we know the partial derivative with respect to y is 1 divided by 2x plus y. So now that we completed step 1 in finding the partial derivatives of the multivariable function, for step 2, we're going to evaluate these at the point. So I'm going to make a line to separate the work we've already done. So for step 2, we evaluate the partial derivatives at the point. And what point are we choosing? Well, it's the point that was given in the problem. So in this case, negative 1x, positive 3y. So what we do basically is literally just plug in x and y for partial x and partial y. So in doing so, when we do that, the partial derivative with respect to x evaluated at negative 1 and positive 3 is equal to plugging in just x and y. So we have 2 divided by 2. The x term is negative 1 plus the y term, which is 3. And this is equal to 2 over negative 1 times 2 plus 3. Minus 2 plus 3 is 1. So this in turn is equal to 2. So f of x, so partial x evaluated at the point is 2. What about partial y? Well, we do the same thing, except now we're just going to plug in the y terms. We're going to plug in with respect to f of y. So 1 divided by 2x plus y. We have the same denominator, so the denominator should be 1 as well. The numerator is just 1. And when we plug this in, we get 1 over 1. And the partial derivative of y evaluated at the points would simply just be 1. So now I'm going to put a circle around these two because we're going to come back to them. So now for step 3, now that we have found the evaluated partial derivatives, now we plug them into the formula and solve for z. So what formula? Well, this formula right here. Partial z of evaluated at xyz, z minus z naught is equal to partial x evaluated at xyz, x minus x naught plus partial y evaluated at xyz, y minus y naught. And for this particular function, it was only two-dimensional. We only had 2 variables, which were just x and y. So for this case, we're going to solve for z. And you could also be given a point z, and you would just apply z minus z naught. And you would have to take the partial derivative with respect to z. And that's if you're given 3 variables. But in this case, we're given 2. So to find the tangent plane and linear approximation, we plug into the formula and we solve for z. So z is equal to the formula z minus z naught. There is no z point. The z is 0. So it's z minus 0, so it's just z of f of x, y, z, x minus x naught plus f of y of x, y, z, y minus y naught. So we know now that z, whenever we plug in the points, we know z is equal to, the original function was 2x plus y. But what's the tangent plane and linear approximation? Well, we have our partial x evaluated at 2. So we plug in 2. And then x minus whatever our point is our point is -1, so x minus -1 plus our partial y evaluated at the point xyz. Our partial y was evaluated to be 1, and then we have y minus 3, and now we simplify and solve for z. So in doing so, we get 2x plus 1 plus y minus 3. Evaluated a step further, distribute the 2, we get 2x plus 2 plus y minus 3. And then taking this a step further, we have two like terms, so we combine them, we simplify them, and we get that z is equal to 2x plus y minus 1. And that's the final answer. So these are very easy. 3 straightforward steps. Step 1, compute the partial derivatives of the multivariable function, whatever function you're given. Step 2, evaluate the partial derivative at the points. Plug in the points for the partial x, partial y, partial z, however many partials you have. Step 3, we plug into the formula and we solve for z. And we got that z is equal to 2x plus y minus 1. Thank you for watching. I hope that was helpful. Hello guys, so in this video we're going to go over how to find the tangent plane and linear approximation given a multivariable function and a point. So without further ado, we have an equation right here. Partial x evaluated at xyz, z minus z naught is equal to partial z evaluated at xyz, z minus z naught is equal to partial x evaluated at xyz, x minus x naught plus partial y evaluated at xyz times y minus y naught. So here we have a function w is equal to x squared plus times y plus z squared over 3 minus e to the x plus the natural log of y. So without further ado, what's the first step? So the first step we do is we're going to go ahead and want to find the partial derivatives with respect to fx, fy, and fz. So in doing so, partial x is equal to 2x y minus e to the x. All I did was just take the partial x with respect to the function. If you don't know how to take partial derivatives, I have a video on that. Without further ado, partial derivative with respect to y is we treat the x squared as a constant, so we have x squared because the y derivative is 1 plus the derivative of the natural log of y, which is 1 over y. And here I guess I'll go over that real quick. So the derivative of a natural log function would be, let's say for example, the derivative of the natural log of y would be y prime over y. What's y prime? Y prime is a derivative of y, which is 1, or whatever constant you have in front of the y, divided by y. So that's how I got the 1 over y in my partial y. Now for my partial x, how do I get e to the x? I got e to the x because I know the derivative of e to the x, and you can apply the exponential derivatives or you can apply the chain rule because they give you both the same answer. The exponential derivative is just a derived form of the chain rule. So I know the derivative of e to the 1x is 1 times e raised to the x. So the 1's invisible, so it's just e to the x. That's how I got the e to the x. So how about z? Partial derivative with respect to z. So I have z squared over 3. So I take the derivative, it'd be 2z over 3. So the partial derivative of z would be 2z divided by 3. We have our partial z, our partial y, and our partial x. So now on to step 2. So what's step 2 to get the tangent plane and linear approximation? Well, we evaluate partial x, partial y, and partial z at the point. And the point is -1, +2, +5. So we go ahead and evaluate this we're going to make note of the point right here, which is -1, 2, and 5. So now I'm going to scroll down a bit. I'll keep these visible because we need them. Partial x, partial y, partial z. And then evaluate it at these points. Don't worry about the z. We'll get there shortly. Right now we're just going to evaluate the partial derivative. So the partial derivative with respect to x, we got 2x times y minus e to the x. So now what we do is we plug in, very easy, right? Plug and chug. So we plug in the x, y, and z respectively into the partial x. So we plug in x where we see x, y where we see y, z where we see z. So in this case, in doing so, we plug in 2, x is -1. Y is +2 minus e to the x. E to the x would be -1. So this answer is 4 minus, since the exponent, note, why is it -1? Well, that's because the exponent of x, or the x term we plugged in for x was -1. So that's why we reciprocated it 1 over e. It can be tricky and it can get people, but just know all I did was just plug in -1 for x. So that x was substituted for a value of -1. So we know our f of x function evaluated at x, y, z is -4 minus 1 over exponent minus 1 over e. So now partial with respect to y. For y, we got x squared plus 1 over y. So x squared plus 1 over y. Plugging in this one isn't too bad. So we know it's -1 squared plus 1 over y. Y is 1/2, so it's 1 over 2. And then we know whenever we square a number, it doesn't matter, negative or positive, it becomes positive. So the sign convention does not matter. So we get 1 plus 1/2. Evaluating this, we get 3 over 2, or 3/2. So that's our f of y evaluated. So what about our f of z? So our f of z, we see is 2z over 3. So that's our f of z. So our partial z. So now we plug in the z, which is 5. So we get 2 times 2 over 3 times 5. Plug this in, we get 10 over 3. So now we have our partial x evaluated, partial y evaluated, and partial z evaluated. So now on to step 3. For step 3, what we're going to go ahead and do is we plug into the formula and solve for z. So in doing so, what I'm going to go ahead and do is I'm just writing out the formula. So partial x, partial y, partial z. The formula that I have up here, this one right here, this is our formula for tangent plane and linear approximation. All I'm doing now is I'm just writing it again down here. So that way we can reference it and we don't have to scroll upwards. So all I'm doing is simply just copying the formula, so we know that the formula of tangent plane and linear approximation is the one I just wrote right here. It's kind of a long one, but it's very simple. So make note of the formula so you can read it. So basically it's just saying that the partial of z evaluated at x, y, z times z minus z naught is equal to the partial of x evaluated at x, y, z times x minus x naught plus partial y evaluated at x, y, z times y minus y naught. So first thing I'm going to do is I'm going to copy the point. that we have. And the point that we have is -1, +2, +5. From here, now we set it up the way we see the equation. So we have a term f of partial z evaluated at x, y, z. And z minus the point z, which is z minus 5. And the partial evaluated at x, y, z is 10/3. And this is equal to the partial evaluated at x, which is equal to -4 minus 1/e times x minus x naught, so x minus -1, which would be x plus 1. And now we have the y term, which is f of partial y evaluated at x, y, z is 3/2. Then y minus y naught would simply be y minus 2. So now from here, all we simply do is literally just simplify it and solve for z. So in doing so, when we simplify, first thing I'm going to do is I distribute every term. I FOIL out the -4 minus 1/e times x plus 1. Then from there, once I'm foiling it out, I distribute the 3/2 with the y term. And I got these values. And then from here, what I'm simply doing is just gathering all the terms together. And then I change the -4 and -3 to have the denominator of 3. So that way when I add both sides by 50/3, we can see we can do it all in one big sum. Then right here, I added 50/3 to both sides, and I got 29/3, because 50 minus 12 minus 9 is equivalent to 50 minus 21, which is equal to 29/3. And now what I want to do is I want to isolate the z, so I multiply everything by the reciprocal of that. I multiply both sides by 3 and divide both sides by 10. And in doing so, I get 3/10. And that's the answer. So basically what I did in a nutshell, step 1, the first thing we always do when we're trying to find the tangent plane in linear approximation is we find the partial derivatives with respect to x, y, z, however many variables we have in the function. Then we evaluate every partial derivative at the points, which is what we did right here in step 2. Then in step 3, we plug it into the formula, and then we solve for z. And these are pretty straightforward. And for this, we got this value right here. We got z is equal to -x plus parentheses x minus x minus 1 divided by e parentheses plus 3y/2 plus 29/3, and all that multiplied by 3/10. And that's how we do the tangent plane in a linear approximation. Thank you for watching. I hope that was